Hello everyone, today we'll perform our third experiment in the DC motor setup. Our experiment for today is position control. So very simple, this DC motor attached to the disc, we want to control the position. You see these two holes, if you want to make them instead of vertical alignment, we want to make them horizontal, for example. So we want to change the position only 90 degrees or even less than that. So can we control the position of this disc? Yes. So the experiment is position control of a DC motor. If you watch in YouTube the last videos of experiments of modeling and speed control, that will make it easy for you to continue the third experiment, position control. So what we do is same as before, same procedure. We open our computer, disk D, we find our motor control, DC motor, and then softwares, we select not modeling, not speed, we open the position control. Double click on this will open the LabVIEW software, and same as before, we need to select our current device, it's device number 2. Now if we run the experiment, we will see that the motor is rotating for some position, and you know that we need to control our time axis and also y axis. So instead of presenting from 9.6 only 2 seconds, let me stop and make this starting from 0 and shows maybe 15 seconds. And in terms of y axis, let's start from maybe 1, less than that, let's 0.5, okay, 0 for example, okay, minus 2, minus 3, and then make it 4, minus 4. Okay, so we have this loops ready. Now we can start again. If I run, so what do you have? We have our DC motor sometimes at +2 and sometimes at -2, and if you look there in the video, you see that the holes are changing from one angle to another angle, right and left, like 90 degrees, 0 and 90, 0 and 90, 0 and 90. Good. In this screen you see also that we have some overshoot. So we try to reach position of 2, maybe 2 radian, for example. So we reach it, but we have some overshoot, and then we stick to that. Some overshoot, stick to that. Some overshoot, stick to that. So let's go back to our screen. This is input, this is voltage input, and this is position output. Reference is the square signal, measured is the red signal. Amplitude is the signal of the voltage. So if we say higher amplitude 3, we will have higher output and higher input. If we say 4, we will have higher value of that, not 35, not 43. Let's just put 2. Let's go back to 2. So we have amplitude controls the input voltage, and that's why we also control the output position. Frequency, you are familiar with this, with frequency. So if we reduce frequency to 0.2, we say that, or we find that our cycles has more time period. If we say that frequency is 0, that means there is no frequency, no repetition, so the position will be constant at one position. And now we see that we have only one overshoot, but measured and reference, they are same. So let's go back and make it the frequency 0.4 as before. That's it. So our objective, we want to study the effect of KB and KD. Last time in the speed control experiment we applied BI control, KB and KI. In this experiment we want to control B and D, proportional and derivative gain, in order to control the position of a speed of a DC motor. So how we perform our experiment, same as normal, same as before. We go back to our computer, disk D, manuals, and student manual. Student manual, it has now 3 sections. We know that section 1 was performing the modeling section, 4.1 is modeling, and then 4.2 speed control. We did them both, 1 and 2, section 1 and 2. Today we're going to have section number 3, which is position control, section 4.3. okay, widescreen. So same procedure, open the experiment, we have it already. Make sure you select the proper device, we did it. Run the system, it's okay. Amplitude, we can set this default value, amplitude is 2. We go back and check, amplitude is 2. Frequency is 0.4, frequency is 0.4, offset is 0, offset is 0. So KB only 2 and the rest are zeros, 0, 0 and 2. So KB, just leave it at 2, KI 0, and KD is also 0. Now we are ready. So the exercise is, we want to change the proportional gain KB by step of 0.25 between 0. We can change, for example, 0.5, 1, 1.25, 1.5, 2 and 4. So we have a range from 0.25 until 4, and we want to examine the behavior of the position with respect to the reference and explain what is happening when we change the value of KB. Very simple. So we will start, this is 2, let's start from 0.5, for example, 0.5, and run. So with KB 0.5, our reference is the blue and our actual value is this. We see that there is a big difference between actual and theoretical or reference value, because of the value of KB is too small, only 0.5. So let's increase this into 0.75. Same thing. What if we make it 1? Almost same thing. Okay, now it's running. Because KB is 1, there is some delay in the system, but at the end it's working. So let me just go back and check. Yes, it's starting from 30. The system response was okay, but we have higher overshoot, and still we have this error between actual and the reference value. So 1.5, for example. Okay, 1.5, it has an overshoot, but it's good in terms of the error. What about 2? So we have higher overshoot. What about 2.5? Let's make this 5 and make this -5. What about 3.5? What about 4? Okay, and stop. So this is 90 seconds. If I go back to 70, for example, or even to 60. Okay, starting from 75, and ending at 95. So each time you see that the overshoot is higher, and you see that the oscillations, you see it's only one overshoot, up and down. Here we have 2 or 3, here we have 4 cycles. That means we conclude that increasing KB, increasing the value of proportional gain, will increase the overshoot and also will increase the oscillations. In terms of errors, it looks similar. This value, the steady state response, this one, they are similar. So the only change, it will affect the transient time, transient response. This, it has overshoot 2 or 3 or 4. So this will be the effect of KB. Good. So describe the steady state error. We did it for volt and also for speed. If we go back to 70, for example, you can see the effect of changing KB, KI, same thing for the voltage and for speed. Type. Now what if we increment the derivative gain, the KD, by steps of 0.01? Same thing we did for KB. So now let's go back and make this the normal default value, and now we will start changing KD 0.01 and run the system. So the same value of 2, but KD now is 0.01, and let's increase this value, increase this value, increase this value, increase this value. Okay, stop. So obviously increasing the value of KD, we had an overshoot. When we increase, then this overshoot is less, is less, is less. No overshoot. Higher values of KD will generate perfect line parallel to this without any overshoot, but still we have an error. So we can conclude our changing of KD from this screen, from 6 seconds to 14 seconds. If I say that this is 6 and the end is 14, you see this is the effect of increasing KD. High overshoot, less overshoot, less overshoot, no overshoot, with different values of KD we mentioned in here, we put in this value. So we can conclude that the effect of KB is something, we did it. Effect of KB, both of them, which one? This KB, we did it, and also KD, we did it. The same thing in the second experiment for peak time and overshoot. Peak time and overshoot can be found from the practical control guide in the section of peak time and overshoot. So if we go back to our manuals, practical control guide, and page 14, I believe, 1 and 4, we will find that peak time and overshoot, and then we will be able to find the peak overshoot. Y maximum minus the difference will give you this PO, and for this time, peak time, we have T maximum, the time of the peak, and T0, the start of the rise, and this will give you the TB. So you can measure them from the graph, or you can calculate them from knowing the value of zeta and omega. So if we have the value of zeta and omega, we'll be able to measure the PO and TB. In our exercise in the student manual, the question is going to that practical control guide, we need to calculate those values, knowing that zeta is 0.5 and omega is 16. That's it. So if we know the value of zeta and omega, we can calculate the PO, peak time, and overshoot percentage. Good. So can we find a proper KB and K? This is not KI, it should be KD, because we are controlling KD experiment. KI, KD. Sorry, KB, KD. So can we calculate the proper values of KB and KD? So instead of just plugging some 3.5 and plugging some values 3.24, and this KD will make it 0.08, and then we check the response. It has small, by luck this is good, but still we have some overshoot. So the question is how I know the optimum best values for KB and KD. In the manual, this is our exercise. So we need to calculate those values by finding the formula from the practical control guide. So if I come here and I search, for example, control F, search for integral gain. Yes, this one. So we can find the KB depending on the value of zeta and omega 0 or frequency and kv is the model we got from experiment number 1, the modeling experiment. You remember we got two values, k time constant, k gain, and tau time constant. So we take this k from experiment number 1 and we plug zeta, omega and k to find kb. We plug omega and k to find ki. The values of zeta and omega are given in the manual. So you have the value of zeta 0.6, you have value of omega is 25, and already from experiment number 1 you have your k value. So simply you can find the value of peak time overshoot, and also you can calculate the kb and kd, and that's it. So if you have kb and kd values, simply you put them, you calculate the values and you plug them here, 3.25 and kd is 1.25 for example, and then you run the system in order to find the response. Of course this is random values, that's just I just put 0.08. So calculating those values, we have our response with kb ki. We capture them and we measure them. So we measure them from screen by zooming and finding the peak, and we compare this measured value with the calculated value. And then same questions as last experiment, what the effect of zeta and effect of omega on the value of kb ki. So we go back to our manual and we say that increasing zeta will increase kb, increasing kb we know that from experiment will make some overshoot, for example. Increasing omega will increase ki, increasing ki will make some delay, for example. And that's it. This is our experiment for the position control. So by now we are done with the 3 sections of our DC motor experiment. We had 3 of them, VIs. So we had the modeling experiment, the speed control experiment, and the position control experiment. And thank you.